When the VIC-20 first came out, its 3 voices of sound brought games to life. Today, we're going to recreate those sounds, not with the original VIC chip, but with TTL logic. By the end of this video, you'll hear the VIC-20 sing with its regular 3 channels of sound. In the next video, we'll push things even further by adding the noise channel for even more retro magic. Let's get started. I've had quite a few people ask if I'm going to build a sound interface for this machine. Now, I'm going to have to admit here, I'm more of a CPU and graphics guy than I am a sound person, so if I make some glaringly obvious mistakes, don't be afraid to let me know in the discussion below. If necessary, I'll make corrections in the next video. I've run out of space on the main board, so I've made this little sideboard which I can connect via a strip header. I've sized this board so that they should both fit side by side in a standard bread bin case. The VIC chip has 4 sound channels, or 4 voices. 3 of them generate square waves with a 50% duty cycle, and each channel is offset by an octave. These 3 channels are called bass, alto, and soprano. The 4th channel is for noise, and this is by far the most interesting one from an architectural perspective. The lower 4 bits of the 9000E register are for volume, and we'll worry about that a bit later. Each of the other channels has its own dedicated register accessible by the 6502. The top bit of each register is an enable signal for that channel. This signal is active high, so the sound's enabled for a given channel when this bit's 1. The lower 7 bits of the register determine the frequency. I've been using the NTSC settings in this machine because it relates closely to standard VGA. For the VIC-20 NTSC model, the clock signal is 14.318 MHz. Divided by 14 gives 1.022 MHz. Now, I've used a 16 MHz clock for the CPU and graphics system, and look, I could probably divide this by 16 to get a 1 MHz signal. I'm pretty sure I won't notice a difference.
Yum yum time. Everybody's gonna get some. Mommy's got your milk, right? Oh, look, just like milk. You won't know the difference. Almost ready. Oh, yummy, yummy. Doesn't that look good? Nice kitty. Kitty. Uh-oh.
But I'm sure the musicians in the audience will, so I'll add in another 28.636 MHz crystal, which is twice the 14.318 MHz oscillator used in the VIC-20, so I'm going to need to divide this signal down. One of the reasons I particularly like the 74HC161 is that it's really easy to make a clock divider that's a non-power of 2. I want to divide by 14 in this case, and the 161 has a terminal count output, which goes high when the count hits 15. If I invert this signal and feed it back into the parallel load signal, which is active low, it means that instead of rolling over to 0 after 15, it'll roll over to the value presented at the parallel input. If I set the parallel input to be 2, then, instead of rolling from 15 to 0, it'll roll from 15 to 2, then count back up to 15. This means there are 14 steps in the cycle. If we tap the terminal count out signal, or output Q3, we've effectively divided our input clock by 14. This one will have a base frequency of 2.044 MHz, which is twice the 1.022 MHz signal I need, but we'll also deal with that a bit later. From this reference signal, we can generate the frequency for each channel. For base, this is 2.044 MHz divided by 256, divided by 255 minus the contents of register 900A. For alto, we first divide by 128, soprano 64. For the noise channel, we divide by 32, and then 255 minus the contents of 900D. Note that I am using twice the frequency than the one mentioned here on this page. I can use a pair of 74HC161s to generate the various frequency taps I need for the channels. Next, let's look at bass again. I want to further divide our signal by 255 minus the contents of the 9000A register. I'll set up a register which reflects the value at 9000A, and I can feed this into a pair of 74HC161s. I can use the same trick of inverting the terminal count out signal and feeding it back into the parallel enable signal. This means the counter will roll over from 255 to the value stored in the 9000A register. I'm getting closer, but we still have a problem. If we look back to our original clock example, if we load 2 into the counter, then we'll count from 2 to 15, which is 14 steps. So the divisor is 16 minus 2, which is 14. With this circuit, the divisor will be 256 minus the value stored in 9000A. But what I really want is 255 minus the value stored in 9000A. I have two options here. One is not to worry about it, which was actually my first instinct, but I decided that it would be noticeable for higher notes. What I can do is add 1 to the value before I store it in the 74HC574 register. This means our count is 256 minus, in brackets, the value of interest plus 1. If we expand the brackets, this becomes 256 minus value minus 1, which is equal to 255 minus the value. I can do this with a pair of 74HC283 adders between the memory data bus and the inputs to the register. If I set carry and make one input 0, then we'll add 1 to the value. I still need to be a little careful about the most significant bit from the data bus. According to the spec, this circuit should be disabled for a register value of 127 because the enable bit's clear. But if I add 1 to it, it suddenly becomes 128 or 80 in hex, which is enabled. You can get around this by bypassing the adder with the top bit of the data bus and connecting it directly to the 74HC574. So far so good, but I still have another problem. I want the output to be a square wave with a 50% duty cycle, which means the output is high for exactly the same amount of time that it's low. If I tap the terminal count signal, then I'll get twice the frequency I want, but the duty cycle will be way off for terminal count. If I add in another D-type flip-flop with Q-bar connected to the D input, then it'll act like a toggle flip-flop. It doesn't matter what the duty cycle of the feeding clock signal is, it should produce a nice square wave with the 50% duty cycle coming out of the toggle flip-flop. Finally, I can connect the most significant bit of the register, which is our enable signal, up to the asynchronous clear input of the flip-flop, and we should be good. To generate the clock dividers for the other channels, I just replicate this for alto and soprano, and even the noise channel. I just change the clock input feeding the 74HC161 counters. Now, I need to make some connections to our existing VIC-20 build. I've added in this bridge between the main board and the sound board with pin headers on each side. This is just temporary until I mount the whole thing in a bread bin case. I don't really want to extend the memory bus across this bridge here. It'd probably be okay, but I have a spare 20-pin socket wired in, so I'll just put a 74HC245 octal driver between the memory data bus and the sound card. Again, I probably don't need it, but because some of the traffic on the memory data bus will be 6502 code, it might be super sensitive to a noisy signal. Here's the sound card from underneath. I've already wired up the power and ground signal to each chip. This is a set of 4 74HC574s and 8 74HC161s. These are arranged into bass, alto, soprano, and the noise channel. Unfortunately, I have to wire up each channel individually, but this is where I really miss the copy and paste function we have with printed circuit boards. Each unit's identical, the only thing that differs is the clock frequency driving the counters and the address that clocks the input to each of the 74HC574s. These wires connect the octal D-type flip-flops to the counter. This goes on for a while, so I'll just skip to the end here. The input to each of the registers is basically an expansion of the memory data bus, but remember that it runs through a buffer and a pair of 74HC283 adders, which increments the value by 1. It's a little hard to see here, but the most significant bit going to the registers comes from the input to the adder rather than the output, and this is done to avoid the anomalous behavior when the register is loaded with 127 or 7F hex. Let me just finish wiring up this bus. I'll just wire these signals together through some resistors and feed them into an audio amplifier and connect it up to a speaker. Let's see how it goes. This is just captured with my iPhone, and it's actually quite a bit louder in real life. Remember, I haven't implemented the noise channel yet, so this is just the tunes. But it does appear to be working for bass, alto and soprano. It's pretty close, but not quite perfect. That tune at the start sounded a little off. I'm not going to worry about it for now, but I'll dig into it in more detail in the next video once noise is wired up. I've also got a little more work to do in the graphics, but we're getting closer. Make sure you subscribe so you don't miss it, and as always, let me know your thoughts and questions in the comments below.